Hey guys, this is going to be an audio presentation of the lecture that I've written down and posted as a PDF. I'm not going to vary much from that text in this discussion, so feel free to focus on that and that alone, since this will just replicate that material. A lot of you guys have asked for audio recordings of lectures because you prefer to listen to these things during a drive or at home while doing other things. And since this isn't a very visually um, infused discussion, I think there's no problem with that. So I'm just going to read the lecture here and probably add things as I go because I can't help myself. This lack of discipline is a problem. I think my mother taught me about this, but nevertheless, we're going to try to stick to the text as we go forward. With that in mind, though, it's important either to read this lecture or to review it through this audio file and also read the Chatfield Chapter 5 text. The quiz contains material on both, and some of it doesn't repeat between the lecture and the book chapter. So try to focus on answering questions based on all of the sources for this module. Okay, let's start. One of the reasons I decided to go with this really kind of unconventional textbook was that it had this chapter on abduction. Most classes in critical reading tend to overemphasize, in my view, the critical part of critical reasoning. We look at arguments and we try to deconstruct them or evaluate them in ways that reveal their flaws. And what we don't get is in these examinations is any sense of the creative role of thought and reasoning and solving problems and explaining features of the world. Well, we might say that inductive reasoning is ampliative. It grows our knowledge by confirming particular claims. It doesn't explain the sources of those claims. And abduction, like as a form of reasoning, is sort of meant to account for the creative act where we come up with an explanation, a hypothesis to account for a particular phenomenon. If induction's a leap, it's only because abduction has provided a kind of landing pad. So with that said, my appreciation of this chapter is somewhat muted by the fact that Chatfield doesn't actually credit the founder of this term as its key proponent. It's not uncommon for British philosophers to undervalue American philosophers. In fact, it's very common. But this is frustrating to me, even as a Canadian, because the origin of this term is well known from the work of the American pragmatist philosopher Charles Sanders Peirce. Pragmatism is a philosophical movement which was created entirely within the United States. Sometimes philosophers compare it to jazz, which as a musical movement was formed entirely in the southern US. Peirce was the founder of a view called pragmatism, but he was quickly followed by William James and John Dewey, sort of two of the giants of American philosophy. This movement was extremely significant and can still be seen that way in American intellectual thought. I mean, one way in which it's been particularly important is in judgments from the American legal system. Many of the judges in the 20th century were deeply influenced by this form of thought, including Chief Justice Oliver Wendell Holmes. You know, I'm going off the notes here, but to point out that pragmatism is this idea that what's true or valuable is what works. So whatever solves problems is true. Typically, we regarded truth as agreement with reality, being a representation of the way the world is. Pragmatism says the right view, the view to hold, is the view that solves your individual problems. And I think you can see that's kind of a very American way of approaching things, right? What's the cash value of this particular action? What do I get from this? So Peirce doesn't get the credit for the concept of abduction here. And for what it's worth, in the end, he chose to disassociate himself from pragmatism as well. He had strong objections to the way that various philosophers came to use the term. And because of that, he opted to call his view pragmaticism, which, as he notes, is a name that's ugly enough to, quote, keep it safe from kidnappers. I'd recommend Louis Menon's book, The Metaphysical Club, if you want to know more about the origins of this movement and its impact in American thought. It's very accessible. It's really interesting. And it's a way of sort of doing philosophy, but in the context of a historical background. I think it's a great book. All right, back to Chatfield. So he doesn't start with Peirce. He starts with the British philosopher, surprise, Francis Bacon. Bacon was around in the 1620s or so, or at least that's when he became famous, and he credits Bacon for his advocacy of a way of thinking philosophers call empiricism. Historically, it's been John Locke and David Hume who've received most of the credit for this view. Locke is well known in the United States because his second treatise on government, I think, was part of the basis of the United States Constitution. But he wasn't primarily a political philosopher, not that that matters here. Empiricism is one of those big ideas in the field of philosophy, and it helps define how we approach knowledge and understanding, and it's like an organizing principle. We don't really need to understand it here, but the basic concept, at least for our purposes, is that all knowledge is ultimately the product of our sensory experience. Our minds are populated with ideas that we have gained from our senses. So our first senses of color, texture, and taste sort of form the basic bedrock or alphabet of how we form more complex ideas. We build everything up from these basic sensory concepts, and so they mix together to form complex notions about the world. And the key idea here is that we privilege not any form of innate ideas or reason, we privilege experience. That's how the mind, I think Locke said, this is how the mind becomes furnished, is through experience. Any kind of justification, any kind of proof must be grounded in our experience, right? The basic sense modalities like sight, touch, taste, etc. All right, so let's start considering a few examples. Consider the claim, wet snow is colder than fluffy snow. This is a claim that can be verified one way or the other, but it's one that requires measurement. I need to go outside, of course, when it's snowy, and compare the relevantly different types of snow. I need to find some fluffy snow, I need to find some wet snow, and then take a measurement with a thermometer, which is itself a sensory process. Even the reading of a thermometer is a sensory process. And once I read the numbers, I can confirm any kind of observation. But suppose I say something different. Suppose I say either it is snowing or it is not snowing. Let's, for now, ignore the details of sleet or those other kind of intermediate states. I mean, I think in general, it's either snowing or not snowing. And so let's focus on that. If I say that, if I make that claim, I don't need to go outside to determine its truth, because either way it's true. If it's not snowing, it's true. If it is snowing, it's still true. So it's true either way, so no observation is necessary. That's a logical question, right? That's what reasoning can give us. It can use the implications of our thoughts and ideas and sort of chase out their consequences. This is one of those cases. And we can start to see the difference between what we call the formal sciences like math and logic and the empirical sciences. Logic and math rely on proofs to keep your hands astonishingly clean, right? It's just not the case with traditional sciences like chemistry, physics, and biology. And indeed, even the social sciences, where you might not necessarily get involved in sort of the dirty nitty-gritty of a scientific experiment, you might use forms and questionnaires and other types of behavioral testing. But even granting these, all of these involve collecting evidence about the world. For any empiricist, any real knowledge comes from experience or experiment. On their own, of course, measurements and observations don't tell us much about the underlying nature of the world. If we want to understand, we want to get beyond appearances, we need to develop theories that explain how these ideas are related. But we don't have those theories straight from induction. It's not, we can make generalizations, but how things work, how we explain things is going to require a different form of reasoning. This is the role of abduction. So let me give you a couple quick examples. And abduction is a broad category. It's not just science, but it actually includes all sorts of observations and inferences we make in our everyday life. So let's do this quick example. This is a normal frustration for me. Every time I go to retrieve my laptop from the charger, it's been unattached. I know that I put my laptop there. I know that I plugged it in, but it's been unplugged. What could explain this? The simple observation doesn't tell me anything except that when I get to work, I will need to plug in my laptop, or if I'm doing a presentation, I'm going to run out of power in the middle. So I might try to explain this event based on other things I know. Could it be squirrels. There's lots of squirrels in my neighborhood, but no, they rarely get into houses. And besides, they use Windows machines. They don't use Macs. So I don't think it's a squirrel. Could it be getting unplugged by the wind inside? I don't think so. By a weak connection, maybe? By gravity? I suppose that after I consider all these things, I might conclude that it's ghosts. Maybe ghosts come in and unplug my computer. But I also have a daughter, and she doesn't really care a lot about the niceties of who was there first or who plugged in their machine first or who works for a living, right? So I can ask again, right? Is it ghosts or the kid who always unplugs my phone to charge her own like every freaking day? And so when I compare these two hypotheses, we have to make a kind of decision about which one's more plausible. What's the best explanation? In fact, abduction is sometimes called inference to the best explanation. So it moves us considerably beyond the evidence. I haven't seen my daughter do this. I don't know that she's doing this, but it is constrained by several factors. In fact, one of those factors is what we call Occam's razor. Chatfield talks about this too. So we're trying to pick between two different hypotheses that are trying to explain things like how does my laptop charger or how does my laptop get unplugged whenever I try to charge it? We might want to use something like Occam's razor. Now, I'm sure many of you have heard about it. I was taught this idea in my early undergraduate logic classes, and he characterized the principle basically as cut the crap. And in a way, that's the shorthand version of this. It says, let's eliminate any unnecessary or complicating factors when seeking an explanation. In Occam's version, it comes close to plurality should not be posited without necessity. What that means is that when you try to explain something, don't multiply the number of things used to make the explanation unless you have to. So let's go back to my example. One of the differences between ghosts and my daughter is that I'm pretty sure that my daughter exists. I mean, where else does my money go, right? So to say that the ghost is unplugging my computer would require at least some reason to believe in ghosts. As yet, I don't have that reason. However, it doesn't mean that ghosts didn't do it. My daughter could have been on vacation with friends, right? It's possible, I think. But I'm not sure ghosts are even the next best guess. Let's go back to that weak connection example. But as I eliminate alternatives, I might be able to generate better reasons for a more complicated explanation. But in the short term, I opt for the simplest. Sometimes Occam's razor is described as a theoretical virtue, right? That simplicity of a theory makes it a better theory than a complex theory that explains the same thing, in part because it's got fewer moving parts, fewer premises that it relies on that could go wrong. Chatfield offers some examples of scientific reasoning to bolster his case that abduction is a kind of reasoning. My personal favorite involves the biologist Alexander Fleming. In 1928, Fleming had gone on a trip or a vacation to Cancun. I don't know, sorry. But he returned to his lab only to find that most of his petri dishes had been spoiled, that something had got in them and that started to grow. And so even though he had all this bacteria that he was doing experiments on, now they all seem to be showing some signs of mold. Right? So we're at the level of induction here. We've got a lot of samples. We see a lot of mold on these plates. And he asked himself the question, what's going on with these plates? What's causing this? And ultimately what he noticed is that there was a film between the mold and the bacteria, which suggested that there was something in the mold that was killing the bacteria. And once he recognized this, he started experimenting on the mold, only to realize that it was very effective at killing bacteria, which of course is one of the main causes of disease. And this led to the discovery later of penicillin, which is perhaps the single greatest life-saving medical discovery at all time. Fleming was confronted with evidence. He made a hypothesis that the mold was in some way affecting the growth of bacteria. And because of that, he was able to scientifically confirm its role in killing bacteria and halting most kinds of disease caused by bacteria. Okay, so what abduction adds to our reasoning toolkit might best be described in terms of why questions. As phenomena are observed, the observations themselves are inert. They sort of sit there. But we may, as we do with induction, we might postulate that these cases might be part of a generalization, but they don't tell us how or why any event might be taking place. Abduction seeks to unify our understanding of events by finding this common thread, an explanation, essentially, that best accounts for what we have found. It's looking for that underlying cause that unites the evidence and makes a consistent picture. Of course, without further evidence, if Fleming hadn't gone on to do further experiments, abduction offers us insight but not proof. So if we think about deduction as certain and induction as somewhat uncertain, abduction is even more uncertain. It needs experiment. It needs induction to back it up. So while we might employ theoretical virtues like simplicity, abduction on its own can't establish a scientific theory. Instead, we need to examine the proffered explanation and derive some observable consequences from that explanation. This will involve deduction. We have to see what the logical consequences of a theory are. So what does the theory imply about the explanation? Famously, when Einstein first proposed the theory of general relativity, it lacked any method of experimental verification. So he painted a beautiful picture of the way the universe worked, but it was so difficult, so abstract, that finding a place where his theory actually touched the observable world for humans was nearly impossible. But it was working with the theory and examining its logical consequences that we were able to find some spots of contact between the theory and our observable world. One of these predictions involved the so-called precession of Mercury, which is like a slight wobble in that planet's orbit around the sun. By aligning the predictions from Einstein's gravitational theories and the observations of astronomers, scientists were able to offer an inductive confirmation of that theory. They did another one, by the way, where because Einstein talks about how time moves at different gravities or at different speeds, they put a very precise clock on an airplane and they spun it around the world many, many times to see if there was some difference between the clock on the airplane and on the ground. And that actually showed also that Einstein's theories were correct. So we might develop a kind of a model that goes from abduction to the deductive consequences plus inductive confirmation, ends with a scientifically confirmed theory. I mean, this wasn't the only way that we can talk about theories and how they're proved, but this model of moving from induction to deduction to induction is one that you see repeated throughout scientific history. And again, history of understanding laptop chargers as well. Okay, some theories are obviously not predictive, or rather, they don't predict things in ways that we would find easy also in other ways to confirm. Famously, the theory of evolution, which purports to explain the biological processes by which evolutionary descent occurs, is primarily backward looking. It looks at what happened in the past more than it looks at predictions of what will occur in the future. So because of this, it was difficult to deduce the kind of confirmatory observations that would necessarily establish the theory conclusively. In fact, many skeptics of evolutionary theory base their objections to the theory on this issue alone, right? It's not confirmable. Nowadays, I think they've developed methods and techniques and the use of what they call retrodiction, what we should find looking in the fossil history if this theory is correct. And of course, the overwhelming consensus now is that the evidence has established conclusively that the theory is verified. I think one last point about abduction is also worth making, is that Darwin's theory wasn't the most obvious one. The French biologist Jean-Baptiste Lamarck argued evolution proceeded through the exertions of animals during their lives. So as a giraffe stretched its neck to reach the tallest leaves on the tree, those changes in its body, that stretching, led to a pressure to create offspring that had longer necks. So rather than evolution by genetic descent, this was evolution by acquired characteristics. In many ways, this is the simpler theory, and in some ways it seems more obvious that the changes you would wrought in your current life would have more of an impact on your offspring than something you were born with in terms of your genetic capacities at birth, right? It was not an unpopular theory in the 19th century. However, the central problem with it, and what made people opt for Darwin, is that there was no capacity to explain how those changes during your life were passed on to your offspring. And because of that, Darwin's theory became the more popular alternative because it did have a mechanism that you could understand, a mechanism that could explain why certain genetic features were passed on, others weren't. So none of the explanations of Lamarck's theory were as compelling as that of natural selection. The emphasis on science here is a bit misleading, since the kinds of explanations and theories we develop about the world are not limited to those that are defined by the scientific method. We explain things every day, and we rarely resort to double-blind experimentation to confirm our theories. And part of this is that most of our theories are prosaic. They're kind of everyday things that we explain on the fly to sort of solve the problem that's presented to us in that moment. So let's try and do Chatfield's categories without resorting to the theories of evolution or gravitation, these grand theories. Let me just give you a problem. This actually happened to me. I'm driving. It's snowing like crazy. But because it's warm and the highway has been salted, the road is getting more wet than icy. Trucks are kicking up lots of dirty water off the roadway, and it's splashing onto my windshield, and I can't see. Now, of course, the obvious solution is you just hit the arm of the turn signal, and you spritz the front of your windshield, and you use the wipers, and you wipe it away. But I was doing this, and there was no water coming out, and I was like, well, what's going on? I can't see. So I pull over and I'm trying to figure out how to explain this problem. And again, I don't think of grand theories or explanations, but I just want to understand what's going on based on stuff, a more broad theory of what I already know. Our understanding, let's call it a theory of how cars and windshield wipers work. And we know, for example, that wiper fluid is in a tank under the hood that we fill when it's empty. So this generalized theory suggests an explanation. The tank is empty and can't draw any water to dispense. The hypothesis in this case is to spend, as it turns out, about $7 at a gas station to buy wiper fluid to refill the tank. I was literally in shock when I saw that number. But the hypothesis is testable. I pull on the signal level once I filled it to dispense the fluid, but nothing comes out. So even though I refilled the tank, there's still nothing coming out. So my theory and understanding enabled me to reach a testable hypothesis. If I fill this tank up, I could check whether it works. Unfortunately, it turns out my theory was incorrect. The test scenario, my attempting to spray the fluid, demonstrates that it wasn't a lack of fluid in the tank and that was responsible for the problem. So this is an example of falsification, right? You derive a consequence, you create the experience, the experimental condition, and if it doesn't happen, then you know your theory is correct. We've proven what Chatfield calls the null hypothesis. Why did it fail? I failed to account for the cold weather, and it turns out that the reason it wasn't going through the fluid line was because it was frozen. And so once the day heated up a little bit more, the ice on the line melted, and the fluid started coming through, and it worked fine, and I survived, right? This is boring, right? This is mundane. This is kind of everything, that even though it's something that we do every day, it's not something we pay a lot of attention to. And it's frustratingly expensive, of course, to do this kind of science. But it's no different than how science proceeds on its larger, more clinical scale. Be careful to read Chatfield's discussion of science in the textbook to see his observations of evidence, writ small, and how they can be generalized into the scientific method. But these very same generalizations apply to our everyday life and how we make decisions. Okay, let's talk a little bit about evidence and proof. As we saw from our discussion of inductive arguments, the lack of absolute certainty can be accounted for to some extent by using statistical or probabilistic standards of evidence. Essentially, we can characterize the preponderance of evidence relative to the likelihood of a given hypothesis being true. The goal in such cases is to achieve statistical significance, right? This was on the previous slide. Statistical significance is the probability that a particular result was achieved entirely through chance as opposed to having a noteworthy cause. So we're setting a threshold for significance in a way that gives a standard for how likely the experiment was, the result generated by the experiment was to be by chance or whether or not it tracked a real feature of the world. So when we remove those two blue marbles from a bag, does that imply that the next one will be blue? Not really. You could easily explain pulling two marbles out of an opaque bag by chance. I mean, even if there were 50 different types of marbles in there, the chances that you got two blue ones would not exactly give me really strong reason to believe the next one would be blue. But suppose I pull out 1,000 blue marbles in a row. At that point, I would say I've reached statistical significance. I would be willing to bet that the next marble is blue. That might also be true at 100. So where that line is, we define by what we call the p-value. That's the threshold for when we say it's very unlikely for it to be chance. Now we can move the p-value up and down. Typically, it's around 0.05. And what that means is that there has to be less than a 5% chance that it was by accident or coincidence that something happened before we would say that we have evidence that this is tracking a real property, right? So we're trying very difficult to make we're trying to be very focused on the idea that we need some criteria for saying at this point it's very unlikely to be chance. And keep in mind, if you set the p-value at 0.05, what you're really saying is that this experiment is likely to track a real property 19 out of 20 times. There's still a chance 1 out of 20 times that this result is entirely based on luck or bad luck, I guess, if you're trying to publish. Okay, so p-values are usually defined in advance to avoid what they call p-hacking. In p-hacking, what you do is you change the expected level of probability, you vary it in ways that kind of guarantee that you get a significant result. If you move that p-value around, it becomes less easy, right? Sorry, you can make it more or less easy to prove that something's statistically significant. In fact, research also manipulate and disqualify evidence they gather in some ways to help generate a statistically significant outcome. So when you're selective about how you use your data in these contexts, it's often called cherry picking your data, right? You're choosing only that which is guaranteed to give you a statistically significant result. So one of the reasons, by the way, that when you do a psychological experiment nowadays, you are expected to publish your protocol beforehand to record what your experiment's conditions are going to be before you actually perform it, so that people will have an independent way to verify that you are doing the test in accordance with how you set it up. There are cases, for example, where people will do a psychological experiment, and after they get 10 or 20 trials, which is enough to establish statistical significance, they'll stop if they have a result that they like. They won't keep going because they don't want to risk the pool making their result less significant. So this is a real problem. This willingness to of researchers to manipulate data in just these ways has been thought to be an important factor in what they call the replication crisis in the social sciences. That is, experiments gain credibility and importance to the extent that they can be replicated. This is essentially having another lab redo your experiment to assure that the results are consistent. And what's become increasingly clear, however, is that labs are not replicating each other's work. To choose a personal example, I've been on about 8 or 9 different psychology PhD programs, and all of those dissertations start with an attempt to replicate somebody else's work. In every single case, they failed to do it. They have not got the result of the case that they're trying to replicate. That seems kind of suspicious to me, right? That makes me think that maybe the results generated in the first case are less trustworthy than they should be. So there's a famous saying in philosophy, post hoc ergo propter hoc. It means after, therefore, because of. It often gets a longer translation, but this pretty much covers it. And the idea is that, well, two things may be correlated. One follows the other. One occurs when the other occurs. It doesn't mean that one causes the other. More broadly, we say that correlation doesn't imply causation. And this is a really important question to ask when you make observations about how things are related. Is this a correlation or causation? Defining correlation is actually kind of hard, but we tend to know it when we see it. Two things happening around or near each other, aligning in terms of time or frequency, for example, could all be cases of correlation. Chatfield defines it as two trends that follow each other closely. But that might be saying too much because they can co-occur without following each other. That is, the presence of one might be entirely unrelated to the presence of others. So consider a boring example. Certain insect infestations seem to occur during times of productive agricultural output. That is, we may see larger populations of, say, mayflies when we see greater harvests of apples. So there's a correlation between apples and mayflies. Could we argue that the excess of apples somehow explains or causes the profusion of mayflies, or even vice versa? They happen around the same time. They seem to be plausibly connected, but we don't really know this, right? Because a mere correlation is not sufficient to argue for a cause. After all, something might be responsible for this flowering of apples and insects that's independent of the two of them together, right? So perhaps it's simply a question of getting enough rain for the mayflies to breed. It's also that's propping up the apple orchard crop, right? They may share a common cause, but they don't cause each other. So two things might be correlated, but that doesn't necessarily mean one causes the other. This is an example of what Chatfield calls a third factor, a case where there's an underlying cause that explains the correlation between two unrelated things. Look at Chatfield's other examples in the text. Some of these might feature in the quiz. Chatfield makes a decent case that in many of the circumstances we see causal connections, we are merely making assumptions based on correlations. Indeed, we might find correlations endlessly fascinating, and since correlations are easier to spot than causes are to prove, we sometimes let the correlations speak more strongly for opinion than really we should. Okay, in the final section, I want to just talk briefly about adjudicating research, right? Abduction, we've seen, is about creating hypotheses, and this chapter has largely been about how we test hypotheses. And it might take us a little bit farther afield when we talk about how do we adjudicate experiments, how do we adjudicate scientific theories, even though they're a huge part of our lives, they're a huge part of what we read in the newspaper. We often have people report, oh, I saw in a study that this is good for you or this is bad for you. It's worth being a little bit more savvy about reading the significance into scientific experiments, right? To understand which scientific experiments are the strongest, which are the weakest, for example, right? We all got a chance to see this clearly during the COVID-19 pandemic, where there was this massive scientific effort to solve and understand what was going on. So many of the solutions, circumstances, causes, treatments surrounding the crisis were suddenly published under this sort of wave of studies, all designed to kind of get us to the heart of what's going on, trying to solve the problem. Because in many cases, the studies came to contradictory conclusions, some arguing, for example, that masks were extremely important, to others which said they didn't make a difference in the spreading of the disease. It was really difficult for us as non-scientists to sort of navigate the competing claims about what the best strategies were for handling the disease. Even now, these cases remain controversial, and I don't want to imply that we know everything about what we should have or shouldn't have done when the pandemic started. We don't know everything because a lot of things are quite hard to test. However, like when we approach new studies and evidence, it's important to ask questions about the nature of the experiments being reported. How significant are the results? What was the methodology? What was the p-value, for instance? Many of the questions get very technical, very fast, and it makes it difficult for us to explore them too deeply. We do need to rely on experts to help interpret the results, and we'll talk a little bit later about how we identify experts. But experts often adhere to the same kind of reasoning that we should be employing. So what are the best studies? Chatfield characterizes the gold standard of scientific experiments as randomized controlled trials. These typically involve two groups, half of which are given a treatment, the experimental or treatment group, and another half given a placebo. They're called the control group. Ideally, these experiments are also double-blind, which means that neither the researcher nor the participants are aware which of them are in the experimental or control groups. These are the gold standard because they are designed to precisely measure and control the production of the relevant information. It's done in a way that isolates and eliminates potential sources for bias. These kind of studies, like above all else, have the most predictive power in determining future outcomes. They're less likely to be influenced by extraneous things because they're so carefully designed to sort of blot those out. So we might ask, well, why don't we do all studies this way? I mean, after all, if they're more likely to be accurate, why not limit ourselves to this form of information gathering? Well, the pandemic helped us see exactly what the limitations were for those strategies. They're expensive. They're really, really expensive, especially when we're trying to generate an adequately large sample to prove a particular point. They're slow, and when dealing with the pandemic, getting results quickly was incredibly important. So sometimes we had to sort of move away from these randomized controlled studies. Uh, Sometimes, for example, the only necessary way we could get the data, or rather the only way we could get the necessary data ethically, was to look at cases in the actual clinical settings. We couldn't have a control group if it caused any kind of risk to people to not get a treatment, for example, right? That's a medical ethics class. You should take that class next. Any rate, so we have to use other forms of evidence gathering, right? Some of these are observational studies when we look at actual cases in hospitals or actual cases in terms of ecology or in nature. Some of them are historical. We look at past examples of particular activities to see what outcomes they had. These are much more difficult to control. They're not easy to do blind, but they offer a way of doing experiments, of gathering data that might not be the best possible data for the circumstances. Observational bias might be more common, right? For example, doctors might report some kinds of cases more than others because they're more interesting or surprising or in line with their previous beliefs, so they can be selective. It's much harder to eliminate bias in these cases, but even still, understanding what those biases are is worth exploring and worth understanding that in some cases these results might be overturned by a future clinical trial, right? So many observational studies, especially for medical treatments, have been more optimistic about those treatments than you would find when you did them again with a randomized control group, right, that follows them. Okay, finally, let's finish this. This conversation started with a note about creativity and ends with arguments about proof. Reasoning is about establishing conclusions, where abduction is about generating testable hypotheses. They need each other in this equation, but the tendency is to focus more, at least in classes like this, on confirming our hypotheses than how we create them. Some of this is about psychology. Where does inspiration come from? When I tell a joke, it kind of bubbles into my mind. I don't remember constructing it carefully, It just sort of happens. In a way, a lot of our explanations share this sort of psychological feature of occurring to us. That's not something we can study critically. Then we might prepare our minds by understanding things more carefully, that the correct answer might pop into our heads more easily. I guess we might prepare the ground. Louis Pasteur said that accidents of discovering things happen to what he called prepared minds. Generalized theories of creativity and explanation are much more complex. They're less easy to characterize than the methods we use to confirm them, right? It's easier to do probability than it is to understand how abduction works. So even so, being aware of both the importance and the value of positing explanations, of making inferences to the best explanation, it's also absolutely essential to how we think and how knowledge moves forward, right? So we might not be able to say everything we want to say about it, but we need to understand that it's important and it plays a huge role in advancing science, but also helping explain our daily lives, how we go about making decisions for ourselves and each other. All right, guys, I hope that's enough. And I will try to get a full lecture up next time.